Welcome everybody to this presentation. My name is Daniele Meli from the University of Verona, and I'm going to present this paper about a cognitive framework for surgical task automation in the context of the Autonomous Robotic Surgery project. This project aims at bringing autonomy in the surgical scenario in order to solve some issues as reducing hospital costs or improving the outcome for the patient. In order to do this, we have developed this framework for autonomous task execution based on task planning with logic programming for explainable behavior and reliability, adaptive motion planning based on learning from demonstration with DMPs, and a situation awareness module to provide a semantic interpretation of raw data from sensors. This framework has been applied to the standard benchmark training task of ring transfer with the Da Vinci surgical robot, where the two PSMs, the arms of the Da Vinci, have to place colored rings on same colored pegs, coordinating a number of different actions according to dynamic environmental conditions, which are continuously retrieved from an RGBD camera. As for the task planning module, this is implemented using answer set programming, state-of-the-art in logic programming, which allows to represent a robotic domain in terms of logic predicates and rules over these predicates. For instance, we have the first two lines here, who are causal laws, then implications which match actions with their effects, while we also have a constraint in the last line, which defines that moving to the peg action is forbidden under the condition that the peg is occupied by some ring. And some predicates are fluent, which means that they can change over time, and thus they need continuous monitoring from the RGBD camera, which, starting from a standard color shape segmentation techniques, provides a semantic interpretation of geometric data. And moreover, ASP has the advantage to find always the optimal shortest plan towards the goal. Motion planning is implemented with dynamic movement primitives, which represent any trajectory as a mass spring damper system with a forcing term F. The forcing term is usually defined as the weighted sum of predefined basis functions, and it is learned from human demonstrations in a very fast way with convex optimization. And the forcing term preserves the shape of a trajectory, whatever the starting and goal positions retrieved from the camera are. We have validated this framework in three different scenarios of the ring transfer. In the first one, we have a failed transfer and then replanning is needed. In the second one, we have that colored pegs are occupied, the red and the blue, and thence they must be freed. And in the third scenario, we have the parallel executions of the arm, and an additional ring is added after the end of the task for further replanning. Here you see an example of the learning process for DMPs. We start from 15 human demonstrations of the task. Here, for the moving to ring action, we collect both actions for both PSMs, and then we rotodilate them into the same reference frame from learning of the red dashed DMP. We have finally validated the planning time with standard ASP solver Klingo in 1000 simulated scenarios, and we have shown that our framework is able to perform real-time planning, in particular with parallel execution. Even for longest plans, the planning time is always below 5 seconds. Ongoing research includes learning and refining ASP rules from examples, increasing the repeatability of the framework with visual servoing to reduce the number of errors, and validation against human performances on the same task, and also the implementation with the standard surgical endoscope, which, however, introduces further issues. Thank you for your attention.